Bismillahirrahmanirrahim. In this video, we will discuss two examples related to the magnetic circuits. We have discussed the basics of the magnetic circuits in the last tutorial. So, continuing from there, a magnetic circuit is given to us, that is shown over here. It's a circular core having two pole shoes over here, and a winding is provided over these pole shoes to establish the flux in this structure. You can say this is the stator part of our DC machine, and the rotor part that will be there in the center of that one. So we are going to analyze the outer part of the DC machine, that is the magnetic circuit. Okay, so this core is made up of a material which has the relative permeability of the 5000, and the cross sectional area of this core structure that is given to us, that is 4 into 100 centimeter square. In order to convert it into the meter square for the calculations, you will have to multiply it with 10 raised to power minus 4. So if you multiply it with that, this will be converted into the meter square. And the number of turns over here, N1 and N2 both are equal, and that is equal to 500. And what we are supposed to do, that what will be the flux in this air gap, that is the air gap of 80 centimeter. And in this air gap, in the real machine, you will place the armature or rotor circuit, and that flux will be linked with that one. So at the moment that rotor is not there, and only air gap is over here, so we are going to calculate the flux in this part. Okay, so how the flux will be developed when you will inject the current in this winding, a certain current, let's suppose that is equal to 2 ampere. If you will be injecting 2 ampere in this one, we are going to calculate the flux over here. So the direction of the flux can be determined by applying the right hand rule. By the right hand rule, the flux will be in the upward direction. Curl your right hand fingers in the direction of the current, the thumb will give you the direction of the flux, and that is upward. So flux will be established, and that flux will be divided into two parts at this point. The outer diameter of the structure is 100 centimeter, and the inner diameter of the structure is 92 centimeter. And we have discussed in the last video that for the analysis of the magnetic circuits, we consider the mean length. So the mean length, that is the central length of this part. Okay, so when the flux will be divided into two parts from here, we assume that it will cover this distance. So that will this distance or this length will be used to find out the reluctance of this path, that is R1, and the reluctance of this path is R2, and we will be having a reluctance of this material as well, that is, let's suppose, R3, and the reluctance of this material, it is R5, and the reluctance of this air gap we will be representing with RA. So its equivalent circuit that is shown over here. The reluctance of this part, this is R3, and the reluctance of this path, that is represented as R5, and then the reluctance of this side, that is shown over here, R2, and the reluctance of this side, that is shown over here, R1, and the reluctance of the air gap, that is represented as RA. So we have basically two parallel paths, because the flux is divided into two paths from this point. So one path is this one, so the flux that is coming from here will be divided, let's suppose that is phi 1, and the flux in this direction, let's suppose that is phi 2. So that is coming from this side. So in this we have three reluctances: reluctance of this path, reluctance of the air, and reluctance of that one, and all of them are in series. So those are shown over here in series. And this winding is going to act as a source of MMF, magnetomotive force, that is the product of the number of turns and the current. So this is the equivalent circuit of that one, and in this we will now have to calculate the reluctances based upon the length of the core structure and the length of the air gap in which the flux is going to pass. So what will be the equivalent reluctance that will be seen by this MMF source? That will be the parallel combination of this one and this one, right? R1 and R2, they are in parallel, and then they are in series with R3, R and R5. So R3, R and R5, they are in series, and then the parallel combination of R1 and R2 is in series with that. So the total reluctance that will be seen by this source will be given by this expression. So you can draw the net equivalent circuit of that one. The flux is going to flow when you are going to apply this MMF in this total reluctance R equivalent. Okay. Now let's calculate these reluctances, and for that we will have to look at the mean length that will be seen by the flux when it is passing through that core. So the outer diameter is 100 centimeter, the inner diameter is 92 centimeter. So taking the average of these 200 plus 92, 96 centimeter is the dia of this circle that is marked with the dotted lines, that is at the center of that one. Mean path length is to be considered. So the diameter in terms of meter is 0.96 meter, and of course the radius is the half of that one, diameter by 2. So we are going to consider the mean circular length. So the radius will be, mean radius will be this diameter 0.96 divided by 2, that is equal to 0.48 meter. Okay, so now the circumference of the circle is this distance 2 pi r. So if you take the mean radius, so you will get the mean path length, the total length, but flux is being divided divided into two parts, and as the cross sectional area is same, permeability is same, so basically you can say if you find out the reluctance of this complete part, that will be divided into two parts because of this division of the flux at this point. So what will be the length of this half part? Circumference divided by 2. So let's calculate the total circumference, that is 2 pi r, 2 pi into 0.48, that is from here. So this is the total circumference or the length of the core in meters. So right side length, that is equal to left side length. So L1 and L2 both are equal, and that is equal to L by 2 that you calculated over here. So the length of core for each side is the half of the circumference, that is 1.508 meter. Okay, so knowing this length, now you can easily find out what is the reluctance. The reluctance, as we discussed in the last lecture, is given as length over permeability into area, right? And this permeability will be mu naught into mu r. Relative permeability is given to us, and we will see that how much it is 5,000 times. So it means this core is 5,000 times more permeable than the air. So we will be using that reluctance. We will be calculating the reluctance using this permeability. Okay, so this is the permeability. The length is that one, permeability of the free space, permeability of the material. This was the cross sectional area given to us in centimeter square. This 10 raised to power minus 4 is to convert this one into meter square. So the reluctance of each side is 6,000 ampere ton per Weber. Okay, so we have calculated the reluctance, this one, we have calculated this reluctance. Now we are going to calculate the reluctance of the air gap, that is this path. So reluctance of the air gap, for this the distance is 80 centimeter, that is equal to 0.8 meter, and then only the permeability of the free space, not mu r this time, because we are calculating the reluctance of the air, into the cross sectional area, and neglecting the fringing effect, that is the spreading of the magnetic lines of forces. We say that whatsoever is the cross sectional area over here, same will be considered in this air gap. I am neglecting the fringing effect. If there is a fringing effect that will be given to you, let maybe 5% or 10%, then that may be accommodated while considering the area of the air gap, that may be increased. But over here I am neglecting the fringing effect, that's why I am going to consider the same area as that of the cross sectional area of the core structure. So reluctance of the air gap is calculated like that. Okay, then we need to calculate the reluctance of this path, so this length. So how to find out this length? What is the total length from here to here? That is 96 centimeter, that is the average or the central length, and out of that subtract 80 centimeter of the air gap from here. So rest of the distance is 16 centimeter. So let's divide it equally in two parts, 8 centimeter over here and 8 centimeter over here. So 8 centimeter will be the length of this pole shoe over which the winding is being provided. That's the field winding with respect to your DC motor. So 8 centimeter over here. So now let's calculate the reluctance, 0.08 in terms of meter, this 8 centimeter, and then as this is of a certain material, it has the relative permeability. So you can see mu naught into mu r, this is mu naught, and then this is mu r, and the cross sectional area, and to convert it into meter square, it is like that. So your total reluctance of the this pole shoe is calculated like that, and of course this will be exactly same as that, because we have same cross sectional area, we have same length of the other pole shoe, and same relative permeability. So we have calculated all of these reluctances as we defined over here in the equivalent circuit, and now we are going to find out what is this R equivalent that will be seen by your source. So for that, R3 plus RA plus R5, the series combination, and then it will be in series with the parallel combination of R1 and R2. So net equivalent reluctance can be calculated like that. And then by applying the magnetic Ohm's law, that is F is equal to flux into the reluctance. So from here the flux will be equal to mmf divided by the reluctance. So what is the mmf? As I told you, we are doing this calculation for 2 ampere of the current. If we inject 2 ampere of the current over here, the number of tons are known to us, that is 500 tons over here and 500 tons over here. So total tons will be 1000. So 2 into 1000, so total mmf is 2000, and the total reluctance that we have seen over here. So this will give you the net flux that will be developed, and that will be divided into two parts. So the flux that will be developed will be calculated mmf divided by R equivalent, that is 0.1257 in 10 raised to the power minus 3 or 0.1257 milliweber. So this is the flux in the air gap, and we were supposed to calculate it. If I go and look at the statement of this question, we were supposed to calculate the flux in the air gap for the 2 ampere current over here. So if that is the current, so flux in this air gap we have calculated, right, by developing an analogy between the electrical and the magnetic circuits. Okay, now let's look at another example. This is somewhat that we discussed before, and only the construction is slightly different. Here you have the core structure, and another material is provided right at the center over here. Now here you can see the winding having n number of turns, and the current is being injected in that one. So mmf, that is equal to Ni, will be established, and that will establish the flux, and the flux will pass over this dotted circle. We will consider this dotted circle the mean length of the core in this outer part, and then some of the flux of course will take this loop as well, right. So some of the flux over here, and over here we have the air gap of 1 mm. Now the cross sectional area that is given to us for this core, that is 1 centimeter square, and that will be equal to 1 into 10 raised to the power minus 4 meter square, and the cross sectional area of this central arm is different, that is 0.25 centimeter square. So into 10 raised to the power minus 4, you will get this one in the meter square. And for this air gap, we will consider the cross sectional area of this core part, that is 1 centimeter square. And what we need to do, cross sectional areas are given to us. The required flux density in the air gap is 1 Weber per meter square. So this is what we require over here. We need to establish a certain flux over here. We know that this cross sectional area is 1 centimeter square, so we need a flux of certain flux such that this flux density is established. And the number of tons which are given to us are 1000, in this case 1000 tons. Okay, and calculate the current in the coil. What should be the current? This one, to produce the flux density of 1 Weber per meter square in this air gap. So first of all, let's look at the reluctances. Okay, and we need relative permeability. That is not given. Instead of that, we are given with the H. The magnetic field intensity is given to us. So how to find out the relative permeability? You know that that B is equal to mu H for the magnetic circuit, and considering the relative permeability and the permeability of free space, it can be written like this. So from here we can work out that relative permeability is B over mu naught H. B is given to us, that is 1 Weber per meter square, and mu naught, and then the H that is given to us 1000. So required relative permeability is 795.77. So your core must be this much time permeable than the air, and the permeability is the ability of the material to allow the magnetic flux to pass through it. Okay, so after calculating the relative permeability, now I am going to move towards the calculation. So first of all, I am going to look at the length of this core structure, and for that I need to look at the diameter. The outer diameter is the 20 centimeter, and the inner diameter that is given to us over here is 18 centimeter. So what will be the average diameter? The diameter of the central path, that will be equal to 20 plus 18 divided by 2, that is 19 by 2. So, sorry, this one, for the diameter 20 plus 18 divided by 2, so 19 centimeter is the average diameter over here. So this is the diameter, and for the average radius or the mean radius, the radius of this mean circular path, so 19 divided by 2, so 9.5 centimeter, that is 0.095 meter. Okay, so now we know the flux density that is required, that is 1 Weber per meter square. So we need to calculate the flux. What should be the flux in this branch? So flux is equal to B into A. So magnetic field density is 1 Weber per meter square. Cross sectional area of this part, this is 1 centimeter square, and that will be considered over here. So we need the flux of 1 into 10 raised to the power minus 4 Weber, that is equal to 0.1 milliweber. So 0.1 milliweber flux must flow over here to give you the flux density of 1 Weber per meter square in this arm. So that's what we require. Okay, now let's draw the equivalent circuit of this one. So we will be having core. We have this core. So what will be the reluctance of this part? That will be calculated from this length, starting from this central point to this central point. 18 centimeter is the length from here to here. 0.5 centimeter over here, the mean, and the 0.5 centimeter over here. So total is the 19 centimeter. So this reluctance, this has been marked by this reluctance over here. So I'm going to just reduce the size to just give you one-to-one analogy. So this is being represented as this reluctance R2, then the reluctance of this side starting from here till this point, and that will be equal to half of the circumference of this circle. 2 pi r is the total circumference, divided by 2 will give you the length that will be used to calculate this reluctance, and this reluctance is this R1. And in the series of this, there is the MMF source that is shown over here, that will be equal to the product of N into I. So number of turns are given to us. We need to work out what is the current that is required to establish the flux in the air gap. So for that, for the other side, this is the total length, that is half of the circumference. Out of that, you will have to subtract this 1 mm, and after subtracting this 1 mm, you can work out the reluctance of the core, and that will be R3, and the reluctance of this air gap is RA. So the flux that will be developed over here from your magnetomotive force, let's suppose that is equal to phi, and phi 1, and that is moving like that, right, moving like that, and will be divided into two parts. So the flux that will be going into the central part, that is this one, and the flux that will be going in this path is phi A. So it will be looking at the series combination of these two reluctances, core and the air gap, right, and that is given to us that this flux should be equal to 0.1 milliweber. Okay, now after drawing this equivalent circuit, now let's calculate these reluctances. So reluctance R1, so what is the length for that one? This circumference, 2 pi r divided by 2, half of the circumference, sorry. So that will be equal to pi R1, and the relative permeability we have calculated 795 and mu naught. So the reluctance that is equal to L1 over permeability into A, that can be written like that, and just plug in the values, so you are going to get this reluctance, the reluctance of this side. And then the reluctance R2, that is of central path. So for that you will be considering 19 centimeter, that is the length, mu naught mu r, and the cross sectional area of this part, and that is different, that is 0.25 centimeter squared into 10 raised to the power minus 4 for meter square. So you will be using this cross sectional area to find out the reluctance of this central path, right. So this is calculated, this is calculated. Okay, now what next we are going to do? We are going to calculate this R3. So how to calculate R3? The distance, circumference minus this 1 mm, because that is the air gap over here. That is not to be considered as a part of that one. So pi r, half of the circumference, minus 1 mm divided by mu naught mu r A. So plugging in the values, you can work out what is this reluctance R3. And then at the last, you are going to calculate the reluctance of this air gap. The length of the air gap is 1 mm. So using this length, that is 1 mm, that is equal to 0.001 meter. Permeability of the air and the cross sectional area of the air, that is 1 centimeter square, so into 10 raised to the power minus 4 per the meter square. So this will be the reluctance in ampere turns per Weber. Okay, so we have calculated all the reluctances. Now let's look at what will be the MMF between these 2 points, or magnetic voltage between these 2 points. So we know R3, we know RA, we know this flux phi A, because that is 0.1 milliweber, and that will establish the required flux density of 1 Weber per meter square that is required over here. So we know that flux. So we can find out the magnetic voltage between these 2 points. So R3 plus RA into the flux, that will give you the magnetic voltage between, let's suppose this is point A and this is point B. So that is equal to 1093.227 ampere turn. And the same magnetic voltage will be there across this branch because these two are in parallel, right? So the product phi naught into R2, that is the magnetic magnetomotive force or the magnetic voltage across this, must be equal to what you have calculated over here. So phi naught into R2, that must be equal to F1. So phi naught will be equal to F1 over the reluctance of this path. So you know this thing and you know the reluctance of this from here. So you can work out what is the flux over here. So that is 0.1438 milliweber. So the flux over here 0.1438 milliweber, and the flux that we have seen over here 0.1 milliweber, that is required to establish the flux. So what is the total flux? Total flux is to be provided from here. So the total flux will be equal to the sum of these two. So 0.143 milli and 0.1 milli. So the total flux that will be injected from here is 0.2438 milliweber. That is the sum of this and this. Okay, so that is the total flux required. Okay, so this total flux will be provided by this source based upon the net reluctance of this one. And how to find out net reluctance? These two are in series, and then that is in parallel with this R2, and then that net combination in series with this. So R3 plus RA in series, they are in parallel with R2, this one, and then in series with R1. So you will get R equivalent. So you know the values of all of these, so you can work out this value, and that will be this much ampere turn per Weber. So now from here, you know about this total MMF, you know about the total reluctance, so you can work out this current that is required over here. So for that, what you will have to do, this F must be equal to phi 1 into R equivalent, and phi 1 we calculated over here, the total flux that is required 0.2438 milliweber, total reluctance is that one. So this F is 1820.64. This is the MMF required over here. This must be over here. Then required flux will flow over here, that is 0.2438 milliweber, and then 0.1 milliweber will flow in this to establish the required flux density. So you have calculated the MMF that is required. Okay, and MMF is given as the product of the number of turns and the current. So that must be equal to this one. So from here, Ni, that will be equal to 1820.64, and the current will be like this, and this will be equal to 1.820 ampere. So for 1000 tons, over here in this winding, the current that is required, that we have calculated 1.820. So 1.820 ampere current must be injected from the external source in this winding such that it establishes a certain flux, that 0.1 milliweber flows in this branch and establish the flux density of 1 Weber per meter square over here. Right. So if I conclude, what we have done, we have discussed two examples, magnetic circuit examples in detail, at how we can analyze the magnetic circuits. So summarizing this step, first of all, look at the magnetic circuits, draw its equivalent circuit, look at the mean path of the length of the core structure, then calculate the reluctances, and then applying the electrical laws, all those you have discussed in your basic electric circuits course. Apply all of those laws and calculate the magnetic parameters. Current is analogous to flux, or flux is analogous to current. MMF is just like the voltage source, reluctance is just like the resistance. Develop the electrical circuit, apply electrical laws, and solve it, analyze it for any required parameter. So magnetic circuit can easily be solved by the information of the electrical circuits. That's all from this video. Thank you very much.